All right, we will go ahead and get started. Okay, like I said, there's going to be some polling questions, so please do your best to keep up with the lecture and stop me at any time if you have any questions. So I'm going to start up here and remind ourselves what we were looking at before and what we're going to be looking at today. So far in this module, we've covered charge distributions. We've talked about electric fields from charges. Electrostatic potential energy is what we're going to be talking about today. So if you remember, before spring break, we talked about Coulomb's law and Gauss's law. So if you have a distribution of charges, how do you calculate the electric field resulting from those charges? An electric field was basically the idea that wherever you have positive charges, the electric field lines are going to point away from the positive charge. Wherever you have negative charges, the electric field lines tend to point towards the negative charge. And by using Coulomb's law and Gauss's law, you can actually calculate the specific magnitudes and the specific directions of those fields. Today we're going to be talking about the concept of potential energy, electrostatic potential energy, and that's going to be the entire lecture today. So let's get right to it. Go. Okay. So I'll just jump ahead here. Okay. All right, can everyone see my screen now? Give me a thumbs up. Okay, good. Now, in your windows, in your main window, you're going to see my face, and then below that, you're going to see the PowerPoint slide. If you want to maximize the PowerPoint slide, you'll see on the right corner there's a set of 4 arrows, and if you put your mouse over that, it'll say Make Screen Share Full Screen. And if you do that, you'll be able to see the entire PowerPoint slide. So that might make it easier for you. You also have the PowerPoint slides in a separate window. If you want to download it from our Canvas site, you can do that as well. Okay, so I'm actually using a 2-monitor setup, so I will be able to see your questions as they come up. But if you're not, if you put something on there and you need to get it answered, and I haven't answered it yet, go ahead and unmute your mic and ask your question, so we don't, so you don't fall behind. All right, so let's go back to this concept of that you learned in physics. I always like to start from first principles, and we're going to talk about mechanical work and electrical work. So as many of you know, as engineers, whenever you put work into a system, you're transferring energy into that system. So let's first talk about what the concept of work is. In the mechanical domain, work is this idea that when you exert a force on an object and move it through a distance, you're doing work. Okay? If you exert a force on an object, like if the guy is pulling on the barbell, but he's not actually moving the barbell, that is not considered work. He's exerting a force, but that force is not being exerted through a distance. All right, so the object has to move as well. Quick question, can everyone see my mouse on the screen? My mouse is now pointing to, okay, good. Then I won't have to use a laser pointer. All right, so the work has to be forced through a distance. And so if this individual were to move this barbell through a height of 2 meters and you were exerting a certain amount of force in newtons, the work is going to be equal to the force in newtons multiplied by the distance through which that force was exerted. And the units for work, the amount of work that was done, is given in joules. That's the MKS units for work. Now in the electrical domain, a similar effect can happen. In this case, the electric field does work on a particle. The electric field exerts force on a particle, just like this individual was exerting force on this barbell. And the electric field, by exerting force on the particle, it can move it through a distance. The definition of work remains the same. You see we have work, and the subscript E stands for electrical. the electrical work is the force times the distance. And as we've learned in the electrostatics module, the electric force is equal to the electric field times the amount of charge. So what we're looking at here is a situation where you have a field, an electric field between two parallel plates, positive and negative charge, and you have your positive charge here. So the electric field exerts a force on that particle. That force is equal to E times Q. And imagine that that particle being moved through the electric field. So this positive charge is repelled by the positive charges here. So it moves this way. It moves through a distance d, and the amount of work that's done on that particle is equal to E times the amount of charge times d. Okay, so keeping that in mind, we're just going to do just a very simple calculation here. So we're going to do this as a pole. Let me grab my... So work is equal to force times distance. This is going to be equal to E times Q times the distance. Okay. All right, so I'd like for everyone to just do this to get used to the units, and this is going to be a polling type question. So there's 5 different options here. So I'm going to just wait right now, and you all can do this simple problem. The problem is we have an electric field, uniform electric field of 10 volts per centimeter. So E is equal to 10 volts per centimeter. An electron placed in the field moves 1 centimeter. How much work was done on the electron? All right, I'll just wait a little bit until we get the responses here. I'll give you a minute or two to do the problem, and I'll just wait a little bit here. Okay, we'll wait just a little bit longer here. Okay, so I see that, okay, 16 of you have given C as the answer, 4 of you have given B, and 2 of you have given A as the answer. So the correct answer is C, so nice job on that. Oops. All right, so let's just quickly go through how to do this. Work is equal to E times Q times D. Electric field is 10 volts per centimeter. The charge on an electron is 1.6 times 10 to the negative 19 coulombs, and it's moving through a distance of 1 centimeter. Okay, so when you're thinking about units, the centimeters cancel here, and so it's 10 times 1.6 times 10 to the negative 19 coulombs. So this is 1.6 times 10 to the negative 18 volts times coulombs. Now, I just want to make everyone aware the definition of a volt. 1 volt is equal to 1 joule per coulomb. Okay, that's the definition of electrostatic potential. We'll talk about that more later. So this joules per coulomb times coulomb, that cancels, and you're just left with joules. Okay, so the electric field is moving a charged particle through a distance, and the correct answer here is C. Okay, so nice. Good start on that. So now we can talk about potential energy. So you think back to this individual. This individual is picking up this barbell here. He's doing work on that barbell. Okay, so when he lifts it up to a height of 2 meters, he does some work on that barbell. And so when he does a work on that barbell, the system gains energy. So now the barbell has what's called gravitational potential energy in that situation. So this type of energy is called potential energy, when you put work into a system and now the system has some type of stored energy. So some examples of potential energy, the gravitational one. So now the barbell is at a specific height above the Earth's surface. So we talked about how that is, we're going to give an example of that on the next slide. Another example in the electrostatic domain is a charged object in an electric field. I'll give you an example of that on the next slide. A kinetic object can have kinetic energy, so any type of moving object has an energy equal to 1/2 mv squared. A chemical system can have a potential energy, so think about batteries. In a battery, there is potential energy stored in the chemical bonds or in an atomic arrangement. In a thermal system, a heated object has some potential energy that can be distributed to other places. So these are some examples of potential energy. So potential energy can be converted from one form to another. Gravitational or electrical energy, for example, can be converted to kinetic energy. So I think we'll get right to the example of that. Now, let me just make sure there aren't any questions here. Okay. Good. All right, so we went over this before, but I just want to touch on it again to remind you of what the concept of potential energy is. So just imagine that you have a tennis ball that's at a certain height above the Earth. You release that tennis ball, and the gravitational field will exert a force on an object, causing it to accelerate. And so whatever gravitational potential energy that tennis ball had is then converted into kinetic energy as the tennis ball accelerates. So at any point in time, the total energy of the system, E, is equal to the kinetic energy plus the potential energy. So some of the relationships that you may recall from that is the gravitational force on the tennis ball is equal to mass times acceleration, which is m times g, which is about 9.8 meters per second squared on Earth. The potential energy of the ball at a given height is given by mgh. M is the mass of the ball, g is the gravitational constant, and h is the height. The kinetic energy is 1/2 mv squared, where v is the velocity of the ball. So imagine at the beginning, when you first release the ball, the height is at a maximum, so you have the most potential energy. And the ball is moving at a zero velocity, so your kinetic energy is basically zero. The ball will accelerate as it falls, and so this v is going to get larger and larger, and the height is going to get smaller and smaller. So your potential energy goes down, kinetic energy goes up as the ball accelerates towards the Earth. Now in the electrostatic system, the electric field exerts force on a charged particle. The way that we think about that is you have these a parallel plate capacitor, two plates separated by d. You have positive charge on one end of the plate, negative charge on the other end of the plate, and you have a uniform electric field that is generated between the two ends of the plate. Now imagine that you have a charged particle. Imagine that you have a single charged particle near the positively charged plate. And just like the gravitational system, you're going to release that particle. You're going to release that charged particle, and that charged particle is going to be accelerated by the electric field. And so the electric force is in this direction because positive charges repel other positive charges. And we look at the system in a very similar way. The electric field exerts a force on a charged particle, causing it to accelerate. The electric potential energy U is converted to kinetic energy K as the particle accelerates, exactly the same as the gravitational system. At any point in time, the total energy is E equals K plus U. So in this case, what's different is now that it's an electrical system, so we first figure out the voltage, the force, and then the potential energy. The voltage is equal to E times D, force is equal to E times Q. This is FEC and VED that we talked about a few lectures ago. All right, and the potential energy is equal to the voltage times the amount of charge. So you can actually work this out. We're going to talk about that a little bit later. But basically, the potential energy of the system is voltage times the amount of charge. Notice that the distance between the plates doesn't even come into the equation. Okay. The kinetic energy is equal to 1/2 mv squared, same as the other system. So if you release this particle, it'll start going faster and faster and faster. The potential energy will decrease because the particle is moving from high potential up here to low potential down here. So the V is decreasing, the large V is decreasing as the particle moves. The small v, which stands for velocity, is increasing as this particle accelerates downwards. Okay? All right, any questions here? I believe in you, John. I believe in you too. I agree with Joseph. Any questions about this? Rima. Okay. Nope, good. All right, good. Excellent. Okay, so moving on. Quick question here. We'll do another quick polling question. Short answer. 4 choices you have here. Suppose I have a charge near the positively charged plate of a parallel plate capacitor. Which of the following statements is true? So the first option is when I release the charge will not move. You can go ahead and select your answer on the poll. So when I release the charge will not move. That's choice A. Choice B, to increase the potential energy, I can decrease the voltage. Choice C, to increase the potential energy, I can decrease the distance between the two plates. And D, to increase the potential energy, I can increase the charge. So which one of those 4 options is correct? I'll give it another 15 seconds or so. Okay. All right, so I will see the polling results. The polling result says A. Nobody chose A. All right, so that's good. The correct answer is D, by the way. So let's just go through these. When I release the charge will not move. That is not correct because, as I said, there's an electric force on the particle, so the electric force will increase, cause the charge to move. Right, this thing will get accelerated by this field. To the increase, choice B, there's a few of you who voted for B. This is also not the correct answer. To increase the potential energy, I can decrease the voltage. This is incorrect. You'd want to increase the voltage if you want to increase the potential energy. The potential energy is equal to the voltage times the charge. Choice C, to increase the potential energy, I can decrease the distance between the two plates. This is an interesting one. This is also not the correct answer. Choice D is the correct answer. 8 of you chose this one, and 11 of you chose D. And I can see why. The reason why this can be confusing is if you want to increase the potential energy, well, first of all, if you just look at the formula, that's an easy explanation. I can just tell you it's V times Q. But I want to talk about the role of the electric field here, because I think that's where some of you may get confused. You can think if you decrease the distance between the two plates. So let me ask you another question. This is not pulled, but if you decrease the distance, what happens to E? So you can go ahead and just go ahead and put something in the public chat here. Oops. So if you decrease the distance between the two plates, okay, I can see that several students said that the electric field will go down, but interestingly, it's actually not the case. It's the we have this relationship V equals E times D. So the electric field is equal to V over D, right? So if you decrease the distance between the plates, the electric field actually goes up, and the force is equal to E times Q. So the answer to the first question is what happens to the electric field? The electric field actually increases. The electric field increasing means you have a larger force on the particle. So if the force increases, you might think, oh, well, if I have a larger force on the particle, maybe that means I have more potential energy because I have more force accelerating the particle. But this is not the case, because the total potential energy remains the same because you have less distance for the particle to accelerate. So that is the reason why the potential energy is not impacted by the distance between the plates. It's just equal to V times Q, the voltage that was applied to the system. All right, so this is the distance that to increase the potential energy, I can decrease the distance between the plates. If this would be true if this said the electric field. If this was the electric field, then this would be true. All right, so this would be increase. That would make it true. Now this is the correct answer, D. To increase the potential energy, I can increase the charge, right? Because potential energy is equal to V times Q. Okay. All right, so I hope that's clear. Feel free to ask any questions if it's not. All right, now we can talk about deriving the potential energy using the concept of work. So we're going to talk about potential energy in the gravitational system and the electrical system. So now what we're going to do is we had this relationship that we found previously. We said that the potential energy is equal to mgh in the gravitational system. Potential energy is equal to V times Q in the electrostatic system. So where did those relationships come from? All right, so the gravitational system, the way that we derive that, if you remember from your physics class or mechanical engineering type classes, you imagine that you're going to take this ball that's sitting on Earth and you're going to move it up. You're going to lift it up against the force of gravity, and you're going to move it to a distance h. All right, so as you move the ball against the force of gravity, you are putting work into the system, and the work that you put into the system is going to be equal to the amount of gravitational potential energy the ball gains. All right, so the differential work, dW we call, we have this definition of work that you saw earlier, which is just for work is equal to force times the length. All right, so the differential work, which you see here, the differential work, dW, is equal to the force times the differential length. So imagine the ball moving through a small incremental distance dl, and the amount of work that's done in moving the ball through that tiny distance is equal to Fg times dl. This is the gravitational force. So you're moving the ball against the force of gravity. Force is equal to m times g, and you're moving that through a distance dl. So if you want to find the amount of work that was put into the system, you have to integrate the dw. You're going to integrate that from the low point to the high point. All right, so as the ball moves up from here to here. So the way that translates into a coordinate system is that you are going to be, imagine that this here is a y-axis. So we're going to move the ball from y equals 0 to y equals h. All right, so that's why you have your dy over here. So your dl became dy because you're moving along the y-axis. Okay, and you're going to integrate this equation. The dw is just equal to m times g. Neither of these are a function of y, so this can just come right out of the integral. And then the integral of y equals 0 to h of dy is just equal to h. So that's how we got our mg h equation. So that's for the gravitational system. So we're going to do the same thing now for the electrostatic system. So ask the same question, how much work does it take to move a charge from one plate to the other? The same plate here as before. Now what we're doing is we're going to take our charged particle and move it from one end from the negative side over to the positive side. Now remember that the electric field, sorry, let's go one step at a time here. The electric field is pointing downwards, so the positive charge is going to want to go in the same direction as the electric field, but imagine that we are applying a force, an external force, so that we are pushing the particle upwards. So we are applying, we call FEXT, an external force to move this particle against the electric field up to the top here. It's kind of like winding up a spring, really. You know how you have to like pull a spring and you have to exert a force on the spring to get it to lengthen, and then when you release the spring it just goes back to it. That potential energy of the spring gets converted back into kinetic energy when you release the spring. So this is kind of like what's happening here in the electrostatic domain. You're taking this positive charge and you're moving it up against the electric field, against the electric force. All right, and so again you have this equation dw is equal to F times dl, force times differential length. You're moving this against this electric force. The electric force, as we know, is equal to E times Q, and that is multiplied by dl. We do the integration again, same as we did in this case. We're going to integrate it from y equals 0 to d. So here, just imagine that this is y equals 0, and we're moving it up this way, and this is y equals d up here. So we're integrating E times Q dy, and again, there's the electric field in a parallel plate system like this is a constant. So this is a constant, the charge is constant. This is not going to be the case in a lot of the problems that we do later in this module. So just keep that in mind. Right now it's a constant. And here's your dy. You're integrating from y equals 0 to d. And because this is a constant, this comes out of the equation. The electric field is equal to V over D, as we saw in the previous slide. Multiply that by Q. All of these factors comes out of the integral, and then you're just left with a V times Q. So I'll show you just an intermediate step here. You get V over D times Q. And what you have in the integral from y equals 0 to d of dy is equal to d. So these two d's cancel, and you're just left with v times q. So that is the amount of work that you put into the system when you move this charge from this plate to this plate. Okay, and that is why the potential energy is now equal to v times q. So the potential energy of the ball is equal to mgh. Potential energy of that charge is equal to V times Q. So let's look at the similarities and differences between them. A major difference is that the in the case of the gravitational potential energy, it depends on the distance that was moved, this height factor here. Okay, so how far you move the ball above the Earth's surface, that determines how much potential energy you have. But notice in the electrical system here, this doesn't depend on the distance moved. The distance between the plates, never comes into the final answer because it gets canceled out by the mathematics here. So what that's telling us is that you could change the distance between the two plates and it wouldn't matter. You'd do the same amount of work in whether the plates were 10 microns apart versus when they were several meters apart, right? The electric field changes when you have different distances between the plate, but the potential energy does not change. And the way you can think about that is that if the distance between the two plates is very large, then you're going to have a small electric field, and you're going to have a small electric force. So you're going to be exerting very little force to move this charged particle against the field, but you're going to have to move that through a long distance because your d is large. And vice versa, when your d is very small, you're going to have a very strong electric force. So it's going to take a lot of force to move this particle against that electric field, but you're going to be moving through a shorter distance. So in the end, the two kind of cancel out there. All right, questions? All right, good. So now what we're going to do is define this concept of, Arad has a question. Arad is asking, is the work and potential energy directly proportional? The answer to that question is they're actually equal to each other. The amount of work that you put into the system is the amount of potential energy that the system now has. Okay, great. Thank you for that question. Okay, now let's talk about a more general definition of electrostatic potential, because what we did here is we looked at one specific system, the simplest system we can imagine, with just a parallel plate capacitor, a single charge within that uniform electric field. But we have to think about a more general definition that will apply to all situations instead of just the parallel plate situation. And so again, we think about some of the physics here. How much work do we need to do to move a charge through a distance dl in the presence of an electric field E? So we think about the general case where you have an electric field that's pointing in a certain direction. The electric field is pointing in, the electric force is going in this direction. The electric force is pushing the particle in the same direction as the electric field. And the external force that you have to use to move the particle against the field, that's the external force. All right, so in this case, what they do is they set the two equal to each other. That's actually what we did on the previous slide as well. In order to move the particle against the field, you actually have to the force has to be equal to the field. Equal to or larger than the field. So we're just setting them equal to each other here. So F external is equal to negative Fe, and that's equal to negative Q times E. And the differential work is same definition as before, except now we're doing this in vector notation. Notice that this here is now bold. This is bold. This is bold. So these are now vector quantities. These are all vector quantities now. Okay, when you do these on your homework and you want to denote a vector quantity, you can do this. You can put an arrow over it if that helps you. Sometimes when you have a lot of arrows in your work, that can get a little bit cluttered. So you can feel free to leave them out if you like, but just be wary. Be careful of that. It's very easy to show vectors on the computer because you can bold it, but not as easy to do that when you're showing your work on an exam. So be mindful of which ones are vector quantities and which ones are not. Okay, now this. this definition, dW is equal to F times dL, and this is then equal to QE times dL. Okay, the electric field is a vector, the dL is a vector. Okay, let me make a correction here. I made a little mistake here. This is not a vector quantity. This should not be bolded, because work is a scalar quantity, and the units for that is given in joules. It has magnitude, but it doesn't have direction. Okay, so these two are vector quantities. When you take the dot product of two vectors, you get a scalar quantity, and that's your dW. Okay, so to be absolutely clear about this, I'm going to indicate here that this is a scalar quantity. All right, so this accounts for the case, this dot product accounts for the case where, let's say your electric field is in this direction, and you're moving, your external force is in this direction. Let's say they're not lined up like they are here in this diagram nicely. So your particle experiences an electric force this way and an external force going in this direction. So when you take the dot product of these two vectors, it allows you to find the component. It allows you to find the component of the electric field along the direction that the particle is moving. So the dl vector is actually pointed in this direction. It's the unit vector that's pointed in the direction of the applied external force. You're finding the component of the electric force along that vector. Okay, so this allows you to account for any direction of electric field, any direction of external force. So that's why this is a much more general definition. Okay, so now, here we go. So now we're going to talk about the electrostatic potential. So we can define the electrostatic potential as the work per unit charge. As I said before, the units for electrostatic potential is joules per coulomb. Okay, so the relationship between the two can be shown with three different equations. The first one is a definition. This is the standard definition of electrostatic potential. dV is equal to dW over Q. Okay, the change in work divided by the charge. We don't define electrostatic potential as just dW. Okay, gravitational potential energy. In the case of gravitational potential energy, the change in potential energy is just equal to dW. In the case of electrostatic potential is defined as the change in work divided by the amount of charge. So we're normalizing it against the amount of charge. Okay, that's just the way that it's defined. It may make sense to you, it may not make sense to you, but you have to take the amount of work you did and divide it by the charge. That's why the units are joules per coulomb. All right, so the definition of electrostatic potential is that dV is equal to E dot dl. Now this is the differential form of it, and one of the differential forms. If we integrate it, then we get one of the forms that we can actually use for the problems that we're going to do in this class. The voltage is equal to the integral of E dot dl, and we'll see some examples of problems with this, so it'll make a lot more sense when we use it. The voltage is the integral of the electric field. And if you were to now take the gradient of both sides of these equations, you're going to get E is equal to the negative gradient of delta V. Now, the gradient, if you remember, the gradient is kind of like taking a derivative. In vector calculus, you can take partial derivatives, and you can also take the gradient. The gradient is kind of like taking the derivative in all directions. It incorporates the partial derivatives in all coordinate directions. So it becomes a compact way to do differentiation and not have like the dx, dy, dz terms as you've seen in some of the other equations. So if you take this integral form, we're not going to go through the math, but just imagine taking the derivative or gradient on both sides of this. You're going to end up with you take the derivative of an integral and you just get whatever's inside the integral, right? Because the derivative and integral are two opposite operations. So the electric field is then equal to the gradient of the voltage, okay? Like I said, we're not going to go over all the steps of the math. We're just going to take these as rules, okay? All right, so let's go to the next slide then. So we're going to do an example problem now where we find the electrostatic potential difference between 2 points. The electric potential difference is related to the work that's done when you're carrying a charge from one point to another point. So imagine that you have this electric field here, and before we did this simple example where we move P1 from here to, say, up here. We're moving it in this exactly opposite to the electric field, so they both line up. Now we're going to do something where we do something more general, where we move this point 1 to a different point in space, up here, point 2. So we're moving in a direction that's not aligned with the electric field. Okay, so we have to be a little bit more careful on how we do our integrals. So the difference in potential, V2 minus V1, between these 2 points is the work required to move a charge from P1 to P2. Right, so if you imagine like that this is a positive charge here and you're moving it against the field, so you have to put some energy into it to move it from here to here, just like moving against the force of gravity. So the voltage electrostatic potential is related to how much work it requires to move this charge from this point to this point. The way that we solve it is we use the first definition, the integral definition of the electric field, which is the second one, this relationship that you saw on the slide. And when you take the integral, you're always integrating from one location to another location. So what ends up happening is that you end up with an equation like this, where you have two different electrostatic potentials. The difference in electrostatic potential between V2 and V1 is equal to the integral from P1 to P2 of E dot dl. All right, so think about it this way, okay? P2 is at, think about P2 being at a higher electrostatic potential than P1, because P1, we're moving P1 against the electric field, assuming, okay, just think about P1 as having a positive charge, so the force is going downwards, so this P1, we're moving it up to here, we have to move it partly against the electric field. So we have to put work into the system. So the point 2 is going to have a higher potential energy than P1. Okay? All right. So we take the integral from P1 to P2 of E dot dl, as we're, imagine taking a line like this, and that will give you the difference of potential between V2 and V1. So again, imagine a positive charge here, and we're going to move it from P1 to P2. And the amount of force that it takes at any given point is equal to E dot dl. It's going to be equal to Q times E, right? Force is equal to E times Q. At any given point, force is equal to E times Q. And so at every point, you're accounting for the work that it takes to move this charge against the electric field. Now you may be wondering, why doesn't the Q actually show up in this equation? Because voltage is actually the amount of work that it takes divided by the Q. So that's why it's normalized. The Q never shows up in this equation. All right, if you're confused about that concept, don't worry about it. We'll do an example problem, and I hope it'll become clear. So one of the points I want to make up here is this last point that you see here, is that the difference in potential between P1 and P2 is the same. What you calculate here is going to be the same regardless of which path you choose. So, like when you're doing P1 to P2, this is a line integral, right? So you're integrating on a line between P1 and P2. You can imagine that it's, you could have a basic straight line like this. You could have a line that goes straight up like this and takes a 90-degree turn, goes like that. You could take some random line pattern like this and get to P2. It doesn't matter. As long as the field is conservative, an electric field is conservative, then you can take any path you choose, and the difference in potential between P1 and P2 will be the same, regardless of what path you choose. This is true because electric fields are conservative. Conservative fields can be expressed as the gradient of a scalar potential. That's one of the definitions of conservative fields that we found in the vector math module. So you can go back and check that out if you'd like. But because it's conservative, this path independence holds true. So keep that in mind. So if I ask you to solve a problem like this, one of the problem-solving strategies you can think about is which path is easiest for me to do the math on. I would think that it's actually easiest for you to calculate a path like this, where you're aligned with the field, and then in this direction where there's, you're orthogonal to the field and there's no E dot dl is going to be 0 along this path. Right, so because it's path independent, you can think about use strategies like that in your problem solving. Okay, so let's do an example, electrostatic potential difference between 2 points. This is a general example. You have a general electric field, E is equal to x times ax, 2 times ay, 2y times ay. What is the potential difference between P1 and P2? All right, so this is a two-dimensional electric field, or it doesn't have a z component. Let's put it that way. You can think about it as a three-dimensional field, but that just doesn't have a z component for it. And so we're trying to find the potential difference between P1 and P2. Right? This is another one of those types of electromagnetic problems where you're going to have it's multiple parts to it. You have to think through a strategy, and if you're doing this on a test or an exam, show me the steps, and so that you can get partial credit. Homeworks and exams both. So I went through some of this problem, and I can show you the step-by-step process of how to do it. I'll show you on OneNote, but I just want to talk about the strategy here. The first part of the strategy is to parameterize the line that's connecting P1 and P2. As you saw here, we can decide what line we want to integrate along. And oftentimes it's easy to just pick a straight line like this. If you don't know what the field looks like, then if you want to minimize the amount of math you're doing, just pick a straight line between P1 and P2. And we have to parameterize that line. This is an important part that you may or may not have seen before in your math classes, so I want you to see how to do this. The second step is to find the electric field. Well, finding the electric field in this problem is easy. You're given the electric field. Next step is you find dl. This depends on what coordinate system you have. You can use the tables from the vector math chapter to find what dl is. And then you take the dot product of E and dl, so you're finding E dot dl. Choose your limits of integration, and then finally you perform the integral from E dot dl. All right? So you have to think about this in a step-by-step process. Let's go through this one at a time. The answer is a negative 9.5 volts from what I've seen. So let's go through this. Okay, I'm going to go to my OneNote window. Okay, so step one, even before we start the problem, I think it's always helpful to draw the problem. So let's draw this. We're in a three-dimensional space. P1 is negative 2, 0, 0, so let's start with P1. So P1 is going to be located somewhere out here. All right, P2 is going to be at 5, negative 1, 3. So it's 1, 2, 3, 4, 5, negative 1, and then up 3. All right, P1 is located at negative 2, 0, 0. So we have this electric field, and I'm not even going to bother drawing the electric field because it's a non-uniform field. X times AX, it depends on the XY location. So we're just going to move between point 1 and point 2, and we're going to find the potential difference between there. So imagine that we're just taking this path, a straight line path from P1 to P2 like this. All right, so the first step is parameterizing the line connecting the two. And so let's do that. So find equation for line connecting P1 and P2. I don't see any questions yet, so I'm assuming everyone's good. So please feel free to ask questions as if you have them. Okay, so we have these 2 points, and we want to define a vector connecting the 2 points. So we can define this vector by you can call it P2, P1, it doesn't matter. This is going to be, it's a vector and it's equal to P2 minus P1. All right, and so the 3 components of that vector is you take your the coordinates in P2 and subtract out the coordinates of P1. So you're going to take 5. So you're 5 right here, and you're going to subtract out a negative 2. So it's going to be 5 plus 2 times x hat plus minus 1 minus 0 minus 1 times y hat plus 3 minus 0 times z hat. Okay, everyone see how to do that? Give me a thumbs up. Okay, great, thank you. Okay, so the next step is we're going to parameterize this line according to a variable t. So parameterize according to a parameter t. Okay, so the reason we're doing this is a line integral. Okay, it's a single integral. And keep this in mind, this is really important. Whenever you have a single integral like this, dl, you only want to be integrating a single variable. You only want to be integrating a single variable. So how do we define this line in a 3-dimensional space in terms of just a single variable? So that's what we're going to be doing here. So the line P1, P2, we can define according to this parameter t. And so this line is going to be equal to P1 plus t times the vector that we just defined. And the vector, we're just calling it P2, P1. In the book, they refer to this as PQ, which is a little bit more clear, I think. So what we want to do is define this line in terms as t goes from 0 to 1. So in other words, we're going to have some parameter t as we're going from P1 to P2. T is going to transition from 0 to 1. So here, the t moves from 0 to 1. X, Y, and Z are all defined in terms of this parameter t. All right, so so the way that we can define this is going to be negative 2, 0, 0. So this is point P1 plus, so I'm going to put this equal sign here, negative 2, 0, 0 plus t times P2, P1, that vector that we just found. So it's going to be t times 5 plus 2, so this is 7, of course. So 7 x hat minus y hat plus 3 z hat. All right. So a more compact way to say this is just negative 2, 0, 0 plus t times 7, negative 1, 3. Okay. So what we did here is we just, in a really relatively straightforward way, we came up with, we parameterized this line. Now, you can think about this in terms of 3 different equations. If this compact form is a little bit confusing to you, you can think about it this way, is that the x-coordinate, you can put this in terms of 3 separate equations. You can say x is equal to negative 2 plus t times 7, or just 7t. Let's do it. Y is equal to 0 minus 1 times t, so just minus t. And your z is equal to 0 plus 3t. And then your t is going from 0 to 1. So that's how we define this line going from P1 to P2. And so if you use this type of parameterization approach, it will work with any 3-dimensional line. You can have very complex, like helical lines, curvy lines, and you can define 3-dimensional lines in terms of where the 3 coordinates in space, x, y, and z, are all defined in terms of this parameter t. Okay, and the example that I showed you here is how do you define that equation when it's just a simple line like this? All right, but parameterization will actually work for other types of more complex lines too. Okay, so that's the first step. The second step is what is the electric field? The electric field's already given to us. Oh, I see there's some questions. Just a minute. Good question. Song is asking, why is t going from 0 to 1? That is arbitrarily chosen. We chose 0 to 1 because it makes the integration easier. You could define this in terms of t going from 0 to 100. But then you'd have to define your equation differently. So let's look at like why t equals 0 to 1 works well. So let's just imagine that t is equal to 0. All right, let's write this down. I think this will be helpful for everyone. Let's say I'm going to do this over here. So when t is equal to 0, then your x is equal to, so all of these terms are basically 0. So x equals negative 2, y equals 0, and then z is equal to 0. Right, so you're at P, you're basically at this first point. So when t is equal to 1, let's see what happens. So x is going to be equal to negative 2 plus 7 times 1. So 7 minus 2 is 5. y is equal to negative t, so negative 1, and your z is equal to 3 times 1, so it's equal to 3. So when your t is equal to 1, you're at point 2. All right, so if you pick intermediate values of t, let's say t is equal to 0.5, your x is going to be equal to negative 2 plus 7 times 0.5. So this is 3.5 minus 2, so it's 1.5. Y is going to be equal to negative 0.5. And your z is going to be equal to 3 times 0.5, or 1.5. So you'll find that the point that I just described is the midpoint between P1 and P2. So this is a way to use point slope form. When we calculate P1 minus P2, we're calculating, in a sense, some kind of slope going from P1 in order to travel from P1 to P2. And that's why these slope terms appear in multiplied by the t variable, kind of like y equals mx plus b. Does that make sense? Okay, good. Thank you. All right. So let's move on to the next step. Finding the electric field in dl and E dot dl. So the electric field is equal to x hat minus 2y y hat. X hat minus 2y times y hat. dl, okay. dl, we always have to think about what coordinate system we're in. We are in the Cartesian coordinate system. In the Cartesian coordinate system, dl is equal to dx times x hat plus dy times y hat plus dz times z hat. Okay, remember in cylindrical and spherical coordinate systems, you have the r and sine theta terms that you have to worry about. All right, so now E dot dl, you take the dot product of the two. The x terms here, so you have x dx. Then the y terms here, so it's going to be minus 2y dy. Yep, got that. Now the next step we have to do, when we calculate E dot dl, now we have to put everything in terms of t. Why is that? Because it has to do with the limit of integration. Okay, so when we define this integral, hold on one sec here, sorry about that. So we have this v2 minus v1 is equal to the integral of p1 to p2 of E dot dl. So let's write that down. We're going to jump ahead, but we're leaving a space there. v2 minus v1 equals the negative integral from p1 to p2 of E dot dl. So this integral we have to do in terms of t, and the limits of integration for t are going to be from 0 to 1. So let's just, I skipped ahead here, so I'm sorry about that. That's actually step 6. So the limits of integration is going to be t going from 0 to 1. Because of that, now we have to put everything in terms of t. So now we take our E dot dl and put it in terms of t. Let me just move this over here. So E dot dl equals x dx minus 2y dy. So we're going to put this in terms of t. And so let's go back to our equation for t here, and we're going to figure out what x dx and y and dy are. So we have x is equal to negative 2 plus 7t. So we can say dx, if we take the derivative of this equation here, is going to be equal to 7 dt. All right. So our y is given here. Y is equal to negative t. And then our dy, take the derivative of this equation here, and then it's negative 1 dt. All right, so we can put this entire E dot dl in terms of t. And so we'll have negative 2 plus 7t. Our dx is equal to 7 dt minus 2, equation y is equal to negative t, and dy is equal to negative dt. All right. So this is negative 14 dt plus 49 t dt. And this is t, these two negatives cancel, so it's minus 2 t dt. So it becomes 47 t minus 14. And this is all multiplied by dt. Okay, so what we did here, we took our E dot dl and we transformed it into according to our variable t, so that the next step when we do the integral, it becomes a lot easier. Let's see, let me move on here. Okay. So the last step is where we actually do the integration. So v2 minus v1 is equal to the negative integral of p1 to p2. And so as we're going from p1 to p2, we're going to change this in terms of the variable t. So t equals 0 to 1. And E dot dl in terms of t is what we just found, 47 t minus 14 dt. And this becomes 47 over 2 times t squared minus 14t, going from 0 to 1 with a negative sign here. 47 over 2 minus 14. Let me just do that math real quick so you can see it. Hopefully we get the same answer. So this is negative 9.5. Okay, so that's the difference in potential, and the units is always going to be in volts. All right, so it's a multi-step problem, as you can see. Any questions come up? Any points that you did not get? Isa? Okay. All right, thank you, Isa. Okay, good. So really quickly to recap, first thing we did was parameterize the line connecting P1 and P2, and we put it in terms of a parameter T. We have the electric field, step 2, dl, step 3, E dot dl, we just calculated the dot product between the two. In step 5, we said the limits of integration is going to go from t equals 0 to 1, And because of that, we have to put E dot dl in terms of t, the parameter t. And then once you've done that, then the integral becomes very easy because you've already done the work, so to speak. All right, so this matches our answer, so that's a good thing. And we'll just move right on to the next example here. Now, I do want to let you all know that I'm going to go a little bit extra today because we spent the first half an hour going over, going over a lot of the questions and the logistical stuff. So if anyone does have a class afterwards, you can feel free to log off. I won't hold any points against you. But I would like to continue for the ones that are just here. And if you don't have a class, I really encourage you to stay because I think you can learn a lot faster during the lecture while I'm here. You can ask questions versus if you decide to come back and look at this later, it could take you longer and it might be more difficult for you to get the help that you need to answer the questions. So what we're going to do is we're going to talk about the electrostatic potential from a single point charge and then multiple point charges. And I think we'll save charge distributions for another day. So let's see how far we can get in the next 20 minutes or so. So what we're going to do now is derive the electric potential at a distance r from a single point charge. All right, so imagine that you have a point charge here, and then you have an observation point A. All right, and you're going to integrate from a point at infinity, which is assumed to have a zero potential. This is a technique that we're doing. So like the question that we're trying to answer is, if you have just a single charge and you have some distance away from that charge, what is the electrostatic potential at this point, at an observation point? And the technique to do that is you use the equations that we just showed, except what you're going to do is you're going to make one of the points at an infinite distance. So you see how in this example that we did, we had P1 and P2. We had two fixed points here. Here what we're going to do is we're going to assume that one of the points is at some distance r from the charge Q, and then the second point is at an infinite distance away from there. Okay, and we're going to see how that allows us to simplify the equation. So you start out with V2 minus V1, same equation as before. These are all in a line, so you can imagine that this is along the r axis here. I'm going to put that in here. So this is the r axis. So we're going to go from r is equal to negative infinity to r is equal to r, the distance away from the origin. And the dl, because we're in this the coordinate system, we're in this coordinate system, it's going to be equal to dr. Okay, our coordinate system basically is just this one axis. Okay, so r hat dr is the dl vector along that axis. The VA minus V infinity is equal to this thing that you see here. Now, what we know, here's the important thing. This V of infinity is equal to 0. Because you have a point here, right? And that point is creating a positive charge. Or the point is a positive charge, is creating an electric field. So very close to it, you're going to have a lot of electrostatic potential. As you go further and further away, that potential is basically going to die out to 0. So that's why you can make the simplifying assumption that V of infinity is equal to 0. All right, so you have VA minus 0 is equal to the integral of E sub r dr. Took the dot product of these two. And this is where you take the electric field that we found in the previous module. Remember, we found the electric field from a single point charge. We have an equation for that already. It's equal to Q over 4 pi epsilon r squared. So we already have a formula for the electric field, and then we take that, we integrate it from r is equal to infinity to r. And we're going to come up with this, where we have 1 over r and 1 over infinity here. And ultimately we get this equation here. Okay, I went through the math kind of quickly, but I hope that this is something that you can figure out on your own. It's just the basic steps of an integration here. This is the important result. That's why it's highlighted in green here. Okay, VA is equal to Q over 4 pi epsilon R. This next chart shows the electrostatic potential for multiple charges and charge distributions. And there are some example problems that we can do here. You know, I come to think of it, I think that, well, let's just go over a couple of these. Then I want to show you how to use Python on how to plot some of these things. Yeah, I think we can get that done in the next like 10-15 minutes or so. All right, so this is the electrostatic potential from multiple charges and charge distributions. So similar to what we saw with electric fields, we can use the principle of superposition to find the potential due to multiple charges or a charge distribution. And this method is easier than electric fields because V is a scalar quantity. So what we'll do is we're going to start with these two, a single charge and then multiple charges. So if you have a single charge system, you can very easily find the electrostatic potential at any distance from that point charge using this equation Q over 4 pi epsilon R. If you have multiple charges, you have to add up the contributions of each charge. Just like we did with electric field, we said that the total electric field is due to the electric field contributions of all the charges in the system. The same thing holds true for electrostatic potential as well. You can sum up the contributions, the individual contributions of each of the charges of the system to find the total electrostatic potential at any given point. So, the way that you'd go about doing that is just from here, let's say you had multiple charges. So, let's say V is equal to Q1 over 4 pi epsilon R1. And this is the contribution from Q1. And if you have another one, you just add up that second contribution, Q2 over 4 pi epsilon R2. Okay, this is the electrostatic potential contribution from Q2. And so if you just simplify this, 4 pi epsilon, then you have, this would be Q1 over R1 plus Q2 over R2. Okay, and this is the general form of that equation. So this summation is just trying to capture the fact that you can take the 4 pi epsilon terms out of the equation, and then you're just left with summing the charges over the radii after that. Okay. This is an example of a dipole. Dipole consists of two charges with opposite polarity, plus Q and minus Q, which are separated by a distance d. So what we're going to do real quick is find the scalar potential and the electric field of this system. So example of this dipole, we can calculate the electrostatic potential due to Q1, then calculate the electrostatic potential due to Q2, and then sum up the contributions to find the scalar potential. And then we can also calculate the electric field using the relationship earlier, E is equal to the gradient of V. So this solution I'm not going to do by hand. I'm just going to walk you through some of the important parts of it. The most important part and the simplest part really is this part here. Okay, you have two charges, Q and negative Q. Now I'm just going to draw well, I'll just annotate this diagram. So we have this two charges, Q and negative Q, that are separated by a distance d. Okay, and our observation point is way out here. And we're defining that observation point in spherical coordinates in terms of r, theta, and phi. But our definition of the electrostatic potential is very easy. This is just a summation term. So V is equal to 1 over 4 pi epsilon. The summation of n equals 1 to 2, because we only have two charges in this case, of q sub n over r sub n. So we're just adding up the charge contributions. So we have 4 pi epsilon 0. The first charge contribution, the positive charge here, plus q. So plus q over r1. So this is the distance r1. So it's the distance from the observation point to the positive charge. And then the second term here is the charge is negative. And then we have a distance to the negative charge. So we have this R2 line here. Okay. And so you just simplify what's inside the parentheses here, and you get this relationship here. Okay. This is really the main things that I expect you to be able to do in this class. Just a simple summation like this. Okay. Now, if you look at this more mathematically, you can actually find some simplifying assumptions. This is an equation for the electrostatic potential in terms of R2 and R1s and things like that. But if it turns out you can simplify it if you're at a large distance away from the dipole. Okay, I would not expect you to be able to do this on your own. In an exam, this is just it's a known simplification that people use with dipoles, because it turns out dipoles are actually quite common in electrostatics. These types of field lines are actually very common. That's why this system is well known, and some of the simplifying assumptions are also done. So it turns out that if you're at a large distance away from the dipole, large distance means that this r, the distance away from the observation point, is much larger than the separation between the two charges. So in other words, r is much greater than d. If that's the case, then it turns out that r2 minus r1 is approximately equal to d cosine of theta, and the geometry for that is sort of shown here. You can see that r1 is here, r2 is here, and the difference between them is d cosine of theta. And theta is the angle which defines where your observation point is. And then the other simplifying assumption is r1, r2 is approximately equal to r squared. So we're defining r1 and r2 as the distance between the observation point and the two charges, but then this r is the distance between the observation point and the origin. Okay, so we have r2, r1, and r without a subscript, so let's keep that in mind. And when you use these two simplifying assumptions, the electrostatic potential for a dipole simplifies into this equation. Okay, so you can always jot down this equation if you want to know the potential of a dipole. I would probably provide this to you on a test if you ever needed it. Now, the next part of this is finding the electric field. So you guys remember some of the examples that we did in class where we found the electric field from different charge distributions, and it was kind of a pain. If you remember, we had to add up the electric field contributions in the x, y, and z directions due to every single point in the system. And one of the examples that I showed you with Python is that I said, like, when you have situations like this where you have to add up the contributions of many different charges in two or three different directions, like x, y, and z directions, it can become quickly a nightmare to calculate electric field distribution. So before spring break, I actually showed you an example of a Python program that you can use to calculate the electric field lines in three different directions given a set of charges. And in this example, I showed you actually what's called a quadrupole, where you have 4 different charges, 2 with positive charge, 2 with negative charge, and they're arranged in a square-like fashion like this. So this is positive, negative, positive, negative, and we just used a solver to actually calculate the field lines in all 3 directions. So one of the advantages of using scalar potential is that once you've found the scalar potential, then the electric field you can just calculate as the gradient of the scalar potential. So once you have V, you can calculate E in a relatively straightforward manner. In spherical coordinates, the gradient of V, E is equal to the gradient of V with the negative sign by there. And this is the definition of the gradient in spherical coordinates. And so once you start off with the scalar potential, you can easily in 1 or 2 steps figure out the electric field lines. And so this equation that you see here, this equation for the electric field describes this complex field that you see here, where you have these curved field lines like this, and then you have the fringing fields going out like this. It's all described by this simple equation here. All right. So in the spirit of that, I wanted to show you, I think what we can do is we'll end with this one today, and we'll talk about the continuous charge distributions next time. And I'm going to spend just a few minutes on this because I want you all to see how it works, but then I'm also going to upload it to our GitHub page so that you can look at them in detail later. So I'm showing you how to, I'm not going over how we did this previous plot because that was in the previous lecture. I'm going to go through step by step how you create an electrostatic potential plot like what you see here. So same situation as what we had before. We have what's called a quadrupole. Positive charge, positive charge, and negative charge arranged in a grid like this. And we want to find we want to calculate what the electrostatic potential is. Wherever there's higher electrostatic potential, there's a lot of potential energy. So you can see here what the distribution looks like. There's a high potential energy here, and as you go away, it gets lower. So let me just take the next 5 minutes to describe this in more detail. The way that we create this plot is that we first have to create a two-dimensional grid. And what we're doing here is we are creating a grid by defining the x-coordinate is going to go from negative 1.2 to 1.2, and there are going to be 25 points in between negative 1.2 and 1.2. In MATLAB and Python, whenever you work with numerical solvers, you always actually have to create a grid of points in order to work with. So your x and y are both defined as going from negative 1.2 to 1.2. So we choose just like 25 points. If we increase that, it'll take a little bit longer to compute. We won't even notice it. It'll make the graph much smoother. These are one-dimensional vectors, and we need a two-dimensional space, so we use this mesh grid function to create a two-dimensional space from those one-dimensional vectors. And I talked about this more in an earlier lecture, so you can just go for that. Here's where we define the location of the charges in the quadrupole. So this is defining the x and y coordinates of R1, x and y coordinates of R2, and so on. So we have one in each corner of the square. And here we're actually defining what the actual charge values are. So Q1 is positive, Q2 is negative, Q3 is positive, Q4 is negative. Ignore these things after the hashtag. These are comments. The next part is where we actually calculate the electrostatic potential. And all we're doing here is we are literally just using this equation of multiple point charges. There's nothing fancy that we're doing here. We're just adding up all the contributions of each one of those charges. Okay, so here's your 1 over 4 pi epsilon, and then we multiply by the summation Q over R contributions for each one of those. Now the next step here is we create a figure. Just ignore this for now. There's a way that you can calculate the electric field from the scalar potential using the gradient function in Python. I'm not going to go over that today right now. But you're creating a figure here, high resolution figure, 120 dots per inch. The first thing we're doing is we're just plotting where all the points are, where all the charges are. And so we're putting a dot basically at wherever you have the 4 charges. And then we use this contour function. Contour F stands for filled contours. And these are creating contours of the electric field. So it allows you to see the electric field distribution. So when we look at this plot, what you're seeing here is this is the electric field. The color tells you, I'm sorry, not the electric field. The color tells you the electrostatic potential at any given point in space. So you can see that the positive charges, this is a positive charge, this is a positive charge, these have positive electrostatic potential. and the most potential is close to the point, and it drops down as we go further and further away from the point. Similarly, with the negative charges, we have like a very negative electrostatic potential near the negative charges, and it drops and it falls away as we go away from it. Okay, so you can clearly see that you have the two negative electrostatic potentials due to the negative charges and the two positive potentials due to the positive charges. And what's interesting is that right in the middle, right at the center of it, you have zero potential. You have large potentials out here, out here, out here, out here, but you have zero potential in there. And it turns out that this is really cool because you can use this to trap ions, and physicists and chemists use a technique called mass spectrometry to trap ions within these quadrupolar fields. Okay. Some of these other commands, like a color bar, X label and Y label, that's just to make the graph look a little bit nicer. I'm going to show you one more function here. Instead of contour F, if you do contour, and we'll decrease the number of levels to say 20, you'll see a plot that looks like this instead. So the contours are just not filled. This allows you to see lines like this, and every line represents an isocontour. What that means is that everywhere on the line, the voltage is the same. The electrostatic potential is the same at any point along a given line. So, for example, the lines in here, you have high electrostatic potential. As you go further and further out, these lines have correspondingly lower electrostatic potential. And that's all shown by the color bar here. Right? If you have a green line, for example, that's where the potential is close to zero. If you have like a yellow line, that's where you have high potential. But the key point in contour plots is that every point along a contour has the same electrostatic potential. Okay, so in your homeworks, you'll be expected to be able to, make these type of potential plots for perhaps a different charge distribution. Okay, good. So I think we're at 2:30 right now. I really appreciate you all staying extra today so that we can cover material. Next time, what we're going to do is we will go over how to calculate electrostatic potentials from charge distributions, a disk of charge, and then a line of charge. And then what I'm going to do is next time I would like for you all to join VLab. If you don't know about VLab yet, it's a way for you all to remote into our engineering lab computers where we have a lot of simulation software. And so what we'll do in next class is we're going to actually show you how to use COMSOL, which is COMSOL is the one of the de facto tools that's used in industry for doing electrostatics simulations. And so I'll send you directions on how to make sure VLab is set up on your computer, and we can all do some of those examples together as a class starting on Wednesday. Okay, so thanks for your attention, for staying on a little bit extra today. I will be sending you some information and surveys by email, and so please make sure to complete those surveys in the next 24 hours if you can. Okay, thanks for your attention, and I'll see you all next time. Any questions, Arad? Thank you. All right, thanks, Arad. And we'll all, so Hamza, let's have a question. Okay, good. All right, thank you all. The recording will be available on Canvas, and it'll also be posted on YouTube if you have any questions. Okay, talk to you all soon.